Hello, in this video I'm going to be going over calculating the Q, or the amount of energy given off or absorbed during phase changes. So this is from your phase change worksheet. We'll start with some simple ones, like number 2. It says how many joules are required to heat 250 grams of liquid water from 0 to 100 degrees. So I always draw a little heating cooling curve. This is my solid, melting point, liquid, boiling point, gas. And I'm going from 0 to 100. And we're just dealing with water because we know right off the bat that 0 degrees Celsius is the freezing point of water and 100 degrees Celsius is the boiling point of water. If you're given a different molecule, you'll be given the boiling and freezing point. But for the test in this class, you're going to be dealing with water, and your freezing point is always 0 and your boiling point is always 100 for water. We're going from 0 to 100, 0 to 100, and it looks like that covers just one line. Therefore, we're just going to deal with one equation, because each line you can find the energy given off or absorbed with an equation. So each line represents an equation. The diagonal lines represent the Q equals C times M times delta T equation, specific heat equation, and each one has a different specific heat. So you have a different specific heat for ice or solid water. You have a different specific heat for liquid and for gas. So basically every substance has 3 different specific heats depending upon the state of matter in which it is in. Alright, and then we have the horizontal lines, these flat guys, the melting slash freezing point and the boiling slash condensation point. You can find the energy by using Q equals mass times the heat of fusion. That is for the melting freezing point, or Q equals M mass times delta H of vaporization. Both of those values will be given to you, just like the specific heats. Alright, but again, for this problem we're only going from 0 to 100, so that's one equation, and that's the specific heat equation. So our Q equals the specific heat of water, which is 4.184. I'm just going to go with 4.18 joules per gram degrees Celsius. Our mass we're dealing with 250 grams. And our change in temperature is going to be 100 is our final, minus 0 is our initial. So basically it's 100 times 250 times 4.18. Only way to solve that is by using our calculator, the one that we bring to class every day. 4.18 times 250 times 100, and that gives me my answer, which is 104,500 joules. And that is how much energy is given off. And what happens is, like I didn't put my degrees Celsius there, but gram degree Celsius cancels out and joules is left over. That's our unit for Q, energy. That's how you do that one, but how about one that's a little bit different? It says how many joules are required to melt 100 grams of water. Melt 100 grams of water. So we're melting something, we're right here, and it's just, there's just one equation that we're going to do, and that's going to be the mass times heat of fusion. So our Q equals our mass, 100 grams, times our heat of fusion, which they give us is 334. 334 joules per gram. So 334 times 100, just to make sure, 33,400. Joules, grams cancel out, of energy is required to melt 100 grams. Alright, doing one just a little trickier. It says how many joules are required to boil, let's skip that one. Let's get on to something tougher. Alright, how about this one? How many joules are required to heat 200 grams of water from 25 Celsius to 125 Celsius? The heat capacity of steam is 1.84. Alright, I'm going to draw my little heating cooling curve, and we're talking about 25 Celsius. Remember, right, this is 0, that's the freezing point of water, and 100 is the boiling point of water. We're starting at 25, which is within this line that's between 0 and 100, so that's 25, and we're ending at 125, which is in this line that's above 100. So we're going through 1, 2, 3 lines. We're going to have 3 equations. So our first one is Q equals, that's the specific heat one, the diagonal one, so that's the Q equals C times M times delta T. Our specific heat of water, remember, is 4.18 or 4.184. I just like doing that because it sounds better in my mind, so I'm going to 4 sig figs. That's joules, gram degree Celsius. Mass is 200. And our change in temperature, this is where a lot of people make a mistake. They say it's going to be final is 125, initial is 25, but it's not the case because we're just looking at this one line. It ends at 100. So our final is 100 degrees Celsius and our initial is 25. So that gives us 75 times 200 times 4.184 gives us 62,760. And that's joules. And that's just one equation. So now we got to do the heat of vaporization. That's right here. So that's going to be the Q equals mass times heat of vaporization. Our mass is 200 grams. Our heat of vaporization, they gave us in this previous problem 2257 joules per grams, and it's just plug and chug. 2257 times 200 is equivalent to 451,000 joules. Alright, almost done. We have this third one, 100 to 125. That's it. That's a specific heat equation. So that's Q equals our mass of 200 grams times our specific heat of a gas. It's not 4.18, it's 1.84 this time. That's the specific heat of a gas. And we're multiplying it by 125 is final minus initial 100, which is 25. Multiply it. So we'll do 25 times 1.84 times 200. That gives me 9,200. Alright, last step. Take our 9,200, our 451,400, and our 62,760, and we add them all up. And that's going to give us 400 plus 62,760. Final answer of 523,360 joules. So basically what we're saying is if we heat 200 grams of water from 25 degrees Celsius to 125 degrees Celsius, that's going to give us 523,360 joules. That's how much energy it's going to take in order to get us there. And the question is that endothermic or is that exothermic? We got temperature. So if we're going and we're heating it up, you would think it's exothermic, but it's actually an endothermic process because it is absorbing that energy. So you have to input that energy in order for it to increase in temperature. So even though the temperature is increasing, it is an endothermic process. Alright, that is that. Those are the examples, and that's how you do a heating cooling curve.